All right. Hello, hello, my lovely students. So what we're looking at now is section 5.3, which is about polar graphing and polar coordinates. So there are some systems where the data you get comes in a way that doesn't work in an XY plane as well. Think of like a sonar graph, you know how it has the line that sweeps all around and then there's like different pings. So that line is a theta, and then the ping, how far out it is the radius. So that data, like we're getting two pieces of information, but the pieces of information are not an X and a Y coordinate. They're what angle it was at and how far out it was. So that system is called polar because it revolves around a point, which is like called a pole. So polar coordinates are always written in the form r theta. So we get the radius first and then the angle that that occurs at. Which way you kind of consider those when you're going to plot the points is up to you. Yeah. So here I have the point 3 comma pi over 2. And we usually use radians here. So our grid here, the concentric circles are radiuses. So we have 1, 2, 3, 4, 5, 6. So instead of like tick marks on an x-axis, we have these circle ticks. And then our theta are all of the angle lines. So we have like 0, and straight up and down is pi over 2. Way over here is pi. Down here is 3 pi over 2. All right, so there is our 45. And the tick marks are commonly for theta in 15 degrees, which is pi over 12 increments. So basically, like your middle line is still your pi over 4, but each line to either side is our other pretty numbers from the unit circle, pi over 6 and pi over 3. So, and then the same over here. It's like those 3, and those 3. Like those are the measures on the unit circle and where they would go. Even though when we draw the unit circle, a lot of times the space between the 3 of them ends up being equal, it's not actually. There should be more space between pi over 2 and pi over 3 than there is between pi over 3 and pi over 4. All right, now if we're going for plotting some points. So r equals 3. So 1, 2, 3. All right, so that's our r equals 3. And then pi over 2 is this way. So then our point is where those two ideas meet. So there is our first point. So our 2 and pi over 3. 1, 2, and then I find my pi over 3 line and count 1, 2 on it. I usually find the angle first because there's more tick marks to like look through than there is for the radiuses, because you can just like count the radius out on the angle line once you find it. Now, this also brings up an interesting point is, what if something's negative? So it turns out like I could plot the point negative 3 pi over 2. So I'm still looking at that pi over 2, but instead of counting up to positive 3, I would count down to negative 3. So this is just another thing we get to interpret, but it shows up in the graph. So down here are negative 2 pi over 6. So here's our pi over 6 line, which is shared with 7 pi over 6. So there's, just like in trig graphs, how values, there's a pattern and it repeats. With polar coordinates, there are multiple ways to say the same position. So our negative 2 on our pi over 6 line, instead of counting to positive 2 up here, instead, we are going to count back here. All right. So now we've got these down here. Let's go with pink for one, blue for another. All right, so negative pi over 6, just like on the unit circle. Negative pi over 6 is going to be down here. And then we're going to count 3 along that line. So 1, 2, 3. Now our 2 and the 9 pi over 4. So 9 pi over 4, that one's, kind of big. 4 goes into 9 twice with 1 left over. So 9 pi over 4 is 8 pi over 4 plus 1 pi over 4. 8 pi over 4 is just 2 pi. So 9 pi over 4 is coterminal with pi over 4. So the point 2, 9 pi over 4 is the same as the point 2 pi over 4. So here's our pi over 4, and then 2 up. All right, so that is 2 different looking points that are in the same spot in a polar coordinate system. Now, because of the whole negative sign craziness or negative angles, like there's other angles we could talk about here. So pi over 4, if I extend that line, that is also 5 pi over 4. So if I wanted to get to this point, I could say, well, let's go to the 5 pi over 4 angle, but then we're going to count back to negative 2. It's like that is another angle, another coordinate pair that plots the same point. Any coterminal angle, I could keep the radius. If I go pi radians away, then I go with a negative. So I could also, instead of counting to 5 pi over 4, 5 pi over 4 is coterminal with negative 3 pi over 4. So it's just playing around with where is this thing, which way would I count, and it gets me to a particular point. So there are an infinite number of ways to write polar coordinates and be talking about the same position. Now, what we have next is, how does this interact with rectangular? Because most of our stuff we think about and work in a rectangular plane system rather than polar. So we have some lovely equations that we get from this diagram that help us translate between the two. So take that polar grid we have before, and then we can also, the 0, 0 point in the center is our same 0, 0 point in the xy plane. So we're like thinking of superimposing both of them and then figuring out, how do I go from one to the other? So in polar, I measure my angle and then I count my radius out. In an xy system, I count over x and up y. So now we have this r theta set up, but we also have this right triangle that showed up. So Pythagorean theorem, I can see x squared plus y squared is r squared. I can also see that the tangent of theta is y over x. And then if I look at the sine and the cosine of theta, so sine theta is y over r. And then if I just move the r, like multiply both sides, I get r sine theta is y. And then similarly, if we do the cosine of theta, we get x over r, so r cosine theta is x. So we use these four equations when we need to translate something back and forth between. So if I give you an r and a theta, then you can use these two guys to figure out what the x and the y would be for that r and theta. Now, there's a whole bunch of different r's and thetas that'll arrive at the same point. All of them would evaluate to the same x and y value. Now, if I give you an x and a y, one of the polar coordinates you could get by doing Pythagorean theorem and square rooting to get r. And remember, when we square root, there's that plus or minus. So that's why up above we talked about positive versus negative radiuses. And then to get one of my angles, I would have do y over x and then the inverse tangent of it. And then you have to think about, like, okay, I got this theta and I got this r number. It's not immediately obvious, like it's not guaranteed to be the positive of both of those. So you actually have to think about, where does this point end up? Because inverse tangent will only produce angles in quadrant 1 and 4. And sometimes our point is actually over in quadrant 2 or quadrant 3. So we might use the angle we get, but we have to use a negative radius to actually go where we're supposed to be. So going from rectangular to finding a polar can be a little more weird because there's so many ways to write the answer. We're going to give you these formulas on the test. So on exam 3 coming up. All right, so now we're doing, I have polar coordinates, write the rectangular. We literally are going to use those yellow highlighted formulas. So this is r, this is theta. I tend to write that anytime I have polar to remind myself, this is an r and a theta, this is not an x and a y. So x is 3 cosine pi over 2. E cosine of pi over 2 is 0. And the y is 3 sine pi over 2. Sine of pi over 2 is 1. So the polar point 3 pi over 2, 3 comma pi over 2, is the same as the rectangular point 0 comma 3. Now, if we think about pi over 2, that's our vertical up line, and then we count up 3, our x and y tick marks are the same as our radius tick marks. So that point three pi over 2 is the same as don't go x and y and then go up 3. Like don't go x and then go up 3 on the y. Now we have another. Our polar is a -2 for the r and 0 for the theta. Okay, so again, x equals -2 cosine of 0. The cosine of 0 is 1. -2 times 1 is -2. Then we get -2 sine 0. Sine of 0 is 0, so this is just 0. So we get the point -2 comma 0. Coincidence. Like it works for any negative number with 0 as the angle. Then the rectangular and the polar would be identical. But it's like just coincidental that it happens to work. All right, now we've got a -1 and 2 pi over 3. So let's see what happens here. And the cosine of 2 pi over 3 is our 60-degree cosine is 1/2. So -1 times 1/2 is -1/2. Then our y, r, which is -1, sine theta, which is 2 pi over 3, -1 times the square root of 3 over 2. So this is the negative square root of 3 over 2. So -1/2 over negative square root of 3 over 2. So that'd be down. So this is in quadrant 4. So it's actually where 4 pi over 3 would be that point on the unit circle. But that's what happens when our r is 1 or -1 is we're going to get a coordinate pair that's on the unit circle. All right, now here, rectangular to polar, many answers. So let me just start first with, we have x squared plus y squared equals r squared. So they tell us this is rectangular, so I put an x and a y over it to remind myself. So we have 3 squared plus 3 squared equals r squared. So r squared is 9 plus 9 is 18. So r is plus or minus the square root of 18. 18 is actually 9 times 2, so this could also be written as plus or minus 3 square roots of 2. And now our theta Tangent of theta is y over x. So tangent of theta is 3 over 3, which is 1. So when is tangent 1? This is when theta equals pi over 4, or in quadrant 3, 5 pi over 4. So I have two different thetas and two different radiuses, and I have to pick a set that will actually go to the correct spot. So the point 3, 3 is in quadrant 1. So if I pick my small positive angle and my positive radius, I will go there. So that is one of our answers, is the 3 square root of 2, comma, pi over 4. Now, if I also wanted my other answer here, the 5 pi over 4, is pi radians away from pi over 4. So if I go to 5 pi over 4, like I'm in quadrant 3, but if I count negatively on it, I'll go back into quadrant 1. So I could also do negative 3 square root of 2, comma, 5 pi over 4. So those are the two major ways to write this. I can then add or subtract 2 pi to any of those angles and keep my radius the same. So I have like all the ways to write it with the positive radius, all the ways to write it with the negative radius. So it'd be any of these, just plus 2 pi for the angle, or minus 2 pi. All right, that is a good cutting point for this.